All right, let's get our boots muddy today. Welcome to this explainer, Info Engineers. You know, as junior engineers and field techs, you're definitely going to run into situations where all your high-tech gear just, well, it can't save you. Picture this. You've got to transfer a perfectly level elevation mark across a foundation that is just completely obstructed. Your line of sight is totally blocked by columns, scaffolding, maybe a massive concrete wall. That $1,000 laser level sitting in your truck, it's absolutely useless if it can't shoot a straight beam. Or, if the apprentice forgot to charge the batteries. But what if I told you that an 8-pound piece of flexible plastic tubing and some tap water could literally outperform that expensive laser? We're talking navigating right around blind corners with infallible precision. So today we are diving into a masterclass on one of the oldest, yet absolutely most reliable tools in construction, the water level.
Okay, so here's our quick roadmap for today's masterclass. 1. Tools of the trade. 2. The physics of the YouTube. 3. Step-by-step workflow. And 4. Hidden field challenges.
Right, let's jump straight into Section 1, Tools of the Trade.
The absolute beauty of this instrument is its simplicity. You literally just need a few accessible things. First, a length of clear, flexible plastic tubing. I highly recommend a 3/8-inch inside diameter, and we'll get into the hardcore physics of why that specific size actually matters a bit later. You also need regular tap water. And here's a massive pro trick. Add a few drops of red or dark purple food coloring into your bucket before you fill up that tube. I mean, on a bright, dusty construction site, clear water is incredibly hard to read. That dye, it makes the meniscus line pop right out at you. You'll also want a couple of stakes, dowels, or a PVC story pole to mark your measurements, plus maybe some clamps to anchor your reference end.
Think about this. For about 8 quid, or like 10 bucks, you are building a 100% reliable leveling tool. It requires literally 0 batteries, it never ever needs to be sent off for some expensive electronic calibration, and it effortlessly bends right around corners. This is a tool you can just throw in the back of your truck and trust completely.
Moving right along to Section 2, Physics of the YouTube.
Now, as engineers, we don't just blindly follow steps, right? We really need to understand the fundamental forces at play here. The secret behind the water level is a little something called hydrostatic equilibrium. Basically, this is the communicating vessels principle. The ancient Greeks and Romans actually used this exact same phenomenon to build aqueducts that transferred water across massive valleys without any modern pumps. It dictates that an unbothered, incompressible liquid will always seek its own level. Because both open ends of your plastic tube are exposed to the exact same uniform atmospheric pressure pushing down and the exact same gravity pulling the liquid down, the water is forced into a state of perfect balance. To really grasp why this works so flawlessly, let's look at the formula formulated by scientists like Simon Stevin and Blaise Pascal centuries ago. Pressure equals the fluid's density times gravity times the depth. Now, notice what is completely missing from this equation: volume and shape. The pressure at any given depth depends strictly on how far down you go. It is completely independent of whether the tube is curled, kinked, wide, or narrow.
And this brings us to what's known as the hydrostatic paradox. Imagine a narrow tube with very little water volume connected to a massive bucket holding gallons and gallons. Intuition might tell you that the heavy, massive bucket would just push the water right up and out of the narrow tube. But it doesn't, because pressure only cares about depth. Both sides exert the exact same base pressure, creating a perfectly horizontal balance at the surface. So, the takeaway here is that whether you're using a tiny hose or linking 2 gigantic tanks, the water level will always perfectly align at both ends.
Okay, Section 3, Step-by-step workflow. Let's see how this works in the real world. Now that we've got the theory locked down, here is your practical, repeatable workflow out in the dirt. Step 1, and honestly this is absolutely critical, fill the tube and completely purge all the air bubbles. Even a single trapped bubble will break the fluid continuity and ruin your measurement. Step 2, anchor your reference end against your known elevation mark. Just clamp it to a stake. Step 3, walk the working end to where you need the new mark. Now, a really crucial point here for you field techs: if you're spanning a distance longer than an arm's reach, this immediately becomes a 2-person coordination job. You've got to have a partner at the reference end calling out when the water aligns with the benchmark. Step 4, just be patient. Wait for the sloshing to stop completely. And finally, Step 5, mark the align meniscus level.
I really want you to remember the sentiment of this quote: trust the physics. It genuinely does not matter if you're spanning 3 feet across a small trench or 100 feet weaving through an entire house frame. Once that dyed water stops moving, you have established a perfect horizontal plane of reference across your entire site.
Let's wrap up with Section 4, Hidden Field Challenges.
Obviously, we don't work in a vacuum, right? We work on chaotic, weather-exposed sites. So if your water just won't settle or the reading seems off, check these factors. First up, temperature gradients. If half your hose is baking in the hot sun and the other half is in the cold shade, the sun-baked water undergoes thermal expansion. Its density actually drops, which will throw your level entirely off. The solution? Just keep the entire tube shaded to ensure uniform temperature. Next, like we mentioned, trapped air creates a pressure block, so flush the tube completely. Third, capillary action. If your tube is under a few millimeters wide, surface tension literally pulls the water up the sides, giving you a false high reading. That's exactly why we stick to that 3/8-inch tube. Finally, check for kinks. If you're running hundreds of feet of tubing, you've got to perform a visual inspection. Walk your line, ensure the path isn't pinched or blocked anywhere. Oh, and here's a quick pro maintenance tip that will definitely save you headaches tomorrow. Always empty the water level after each use. Never just coil it up and leave water sitting in the tube in your truck. Sitting water breeds algae, it promotes air bubbles, and risks severe thermal expansion issues for your next job. Empty it out and start fresh next time.
So the next time you're staring down an impossible line-of-sight challenge on site, reach for the plastic tubing. I want to leave you with this thought. If a cheap plastic tube driven by ancient physics can outsmart a modern laser level around corners, how else can we apply fundamental science to solve complex site challenges? Don't just rely on the tech. Master the foundational principles behind your tools, and you will never be stuck. Thanks for joining this explainer, Info Engineers. See you on the next site.